All right, to wrap things up, why are ionic compounds important in the body? These are the reason for many of the biological functions we really care about. Muscle contraction, fluid balance, the different electrolytes, constituent ions are really, really essential for such a wide range of biological asks. And when we put one of these ionic compounds in water, it very commonly is going to separate into its ions. And so really just further emphasizing why it's so important that we identify the ions themselves, not just the compound. I think that when we put NaCl, table salt, in water, we see that it dissolves very, very easily. That dissolution is not just turning into a solvated state, but it's actually breaking up the sodium and the chloride into sodium plus and chloride minus, existing in their charged state, overall still neutral from the water. And we'll talk more about that coming up. Here, right, ionic compounds in solid form, these are stuck together. When we're in water, they're broken apart into ions, and we can see this as an explicit chemical reaction here. NaCl-S, denoting the solid state. This is like the table salt on the table. It's in the solid crystalline state. When we put it into water, it breaks up on a molecular level into the sodium ion and the chloride ion. IV fluids and electrolytes work because the ions are free to move throughout solution, and still that solution is neutrally charged because for every one sodium ion we put in, a chloride ion had to come with it. This concept of ionic compounds not just dissolving, but separating, dissociating, is really, really essential for moving forward here in healthcare chemistry. Here's another picture where we have our water molecules. These are our H2Os. This may look a little bit technical, but can highlight why the sodium and the chloride are able to exist so independently, even though they're originally associated with each other. Water has some charged qualities itself. The oxygen is more negative, the hydrogens are more positive, and that's what this little lowercase delta that looks kind of like a curly D that's all over the waters is showing. When we break into solution, these positively charged sodiums and negatively charged chlorides are stabilized by the water, and again, things are looking for more stability. This form on the right, with the water stabilizing the charged particles, is actually more stable than if the sodium and the chloride were to stay associated together. That's why it forms. This is really essential to understand for our biology, as it allows for solvated, free-flowing ions throughout. When we have those ions in solution, we also can have electrical conductivity. These carry an electric charge, and so therefore if we are to try to carry electricity through a solution with electrolytes in it, we can have conduction of that electricity based on the existence of those charged particles. Heart rhythm works because of electrical signals, and so these signals depend very much on these ions moving in and out of cells. And again, we don't need to understand this perfectly clearly at this point, but the idea that these can come from solid associated ionic compounds that dissociate into their individual charged particles in water, and now we have the ions that are part of our biology, leads to many of the things that we really care about, like a heart beating properly, is part of what we're introducing in this nursing chemistry course, and is really essential to really understand for moving forward. ECG, electrocardiogram, this detects electrical activity in the heart, and again, this exists because the ions are moving across the heart cell membranes, and we are able to pick up and detect a signal. With no ions, there's no electrical signal to measure.